swap, and the expected value is 1.25 times what you hold. But that calculation never ever ends. Two identical envelopes sit on the table. One holds exactly twice as much as the other. Who put how much into which envelope, you have no idea. The host hands you an envelope and says, before you open it, you'll get a chance to swap. If my envelope holds 10,000 won, then the other one holds either 5,000 or 20,000 won. The odds look 50-50, an average of 12,500 won, a full 25% gain, so of course you should swap. But run the same calculation on the new envelope, and again swapping is a 25% gain. So you swap again. Never opening a thing, your hand just shuttles back and forth forever. An insane conclusion, yet the math looks perfectly sound. The other person's envelope always looks greener. The title Nailbuff gave his 1989 column. Its sibling Monty Hall wrapped up cleanly. Nail down the assumptions and the answer drops out as 2/3. But the two envelopes is a genuine paradox. 80 years on, countless solutions still compete. We'll take this maze in 6 turns. First turn. Nailing down the rules of the game with zero ambiguity. The stage is bare. 2 envelopes and a promise of double. One holds X1, the other exactly double. A fair coin flip hands you one, and before you open it, you get the chance to swap. The key is the order. The envelopes are filled first, and then one is handed to you at random. That makes the 2 envelopes perfectly symmetric, and this symmetry will be the decisive clue that catches the lie. With the rules nailed down, let's skim the family tree. This puzzle wears many names, but the structure is identical. The oldest ancestor is the necktie paradox of the Belgian mathematician Maurice Krejcik. Both men believe they have the edge. Even if I lose, each says I get the more expensive one. They can't both have the edge. Martin Gardner only popularized it in 1982. The roots trace back to Krejcik. Now let's reason in the first person. I'll call the amount in the envelope in my hand A. Say it holds exactly 10,000 won. Then the other is 20,000 or 5,000 won, each it seems equally likely. Here's the expected amount if you swap. 1/2 times 2A plus 1/2 times A over 2. That works out to 5/4 of A. The problem is that the conclusion is absurd. The exact same logic applies to the new envelope you just swapped for. So you swap again and again, an infinite loop that never ends. And remember, the 2 envelopes were perfectly symmetric. Swapping can't be a gain for both sides. So somewhere in the calculation there must be a lie. And the culprit is hiding far closer than you'd think. Chapter 3. Unmasking the Lie. The culprit, astonishingly, is a single letter. It's true the other envelope holds double or half. The problem is that my money differs between the 2 cases. The trap begins the moment you set your envelope as A and write the other as 2A or A over 2. In the doubling world, the total stake is 3A. In the halving world, 1.5A. 2 games with different money on the table. The 1.25 times calculation threw the 2 into one pot and averaged them, adding apples and oranges. But there is only one real game. The amounts in the envelopes were fixed before it ever began. Fix the envelope pair at 10,000 and 20,000 won. In the doubling case, A is 10,000 won. In the halving case, 20,000 won. The same letter was pointing at 2 different amounts. Logic calls this fallacy equivocation. Instead of the slippery letter A, let's fix the smaller amount as X. The envelopes are X and 2X, just those 2. The smaller one means plus X, the larger minus X. Probability 1/2 each, exactly break even. The right-hand figure is the single real game. Gain and loss erase each other like mirror images. That initial 25% gain was an illusion, measured with a ruler that changed length every time. Measure with a fixed ruler, and gain and loss are both exactly 10,000 won. The conclusion is crystal clear. If you never open the envelope, swapping makes no difference at all. The necktie paradox and the wallet game were exactly the same illusion. If you don't trust the algebra, there's a method both brutish and certain. Just play the game tens of thousands of times. This is the Monte Carlo method. Each round build a fresh envelope pair, then take one by coin flip. Just two strategies, always keep and always swap, and we log the showdown over 100,000 rounds. Keep or swap, the average is about 7.5. The difference is 0.0034, effectively 0. In the left figure, the two curves wobble at first, then get pulled into the same value as the games pile up. The right panel goes one step further. The entire distributions of the final amounts overlap almost perfectly. It's not just that the averages match, statistically, the two strategies are utterly indistinguishable. But so far we never opened the envelope. If you open it and see the amount, wouldn't that give you real information? You open the envelope and see 10,001. Now the other one really is either 20,001 or 5,001. But whatever M you see, can the probability that the other envelope holds 2M really always be 1/2? Bayes answers like this. There are two routes to seeing M, either I hold the smaller envelope or the larger one. The weights are f of M and f of M over 2, so the probability that the other envelope is the larger one is set by their ratio. For this to be 1/2 at every M, f of M and f of M over 2 must be equal at every M. That would mean f is constant on a log scale, its integral diverges, impossible for any proper real-world distribution. Switching pays exactly when f of M is greater than half of f of M over 2. For a decreasing distribution that happens at small m. The actual curve decreases monotonically from 0.9 down to 0.13, crossing 1/3 at the break-even point of about 10.4. Let's experiment with a log normal prior. Both envelopes share the same expected value, 18.28, and the average gain is essentially 0. The gains at small m and the losses at large M, once weighted by the distribution, cancel out to exactly 0. The true heart of this paradox isn't the number of envelopes, it's information and priors, exactly as in Monty Hall. One proviso though, the distribution's expected value must be finite. That one phrase appends everything in the next section. So could we really, deliberately build a distribution where switching pays no matter what amount you see? Unopened, break-even. Opened, still break-even for any proper distribution. A mischievous question opens the door to the abyss. Astonishingly, yes. Mathematicians really did construct such a distribution. In 1953, John Littlewood presented a card version and credited it to Schrödinger. That's as far as certainty goes. In 1995, philosopher John Broome formalized the infinite version. P sub k equals 1/3 times 2/3 to the k. This geometric series sums to exactly 1. A perfectly legitimate probability distribution. If you see 2 to the n, the probability of half is 3/5 and of double 2/5. The expected value is exactly 1.1 times. Except for the lone case of seeing the value 1, every observation gives 11/10, switching always pays. And on the last line, the partial sum has already hit 10 to the 62nd. The weights sum to 1, and at every observed value the green dots sit right on 1.1 times. 1.1 times every time you open one. So is this truly a world where switching forever pays? The trap lies in the expected value itself. The unconditional expectation diverges. Keeping and switching are both infinite. Comparing infinity with infinity is undefined. The very same pathology as the St. Petersburg paradox. The cancellation in the last chapter is a subtraction, valid only when both sides are finite. Broome isn't a counterexample. He marks the boundary of the premise. There's one more exit. As Bernoulli pointed out in 1738, decisions follow utility, not money. Measured in utility, the expected utility converges to a finite value. The half outcome weighs more, so apart from the exception at 1, switching loses every time. Unconditionally, though, it's a draw. The 1/6 probability of seeing the value 1 exactly makes up for the losses. One more note just to get the credits right. The infinite distribution is Broome's. The St. Petersburg connection is Chalmers's. Let's string the scattered history into a chronicle. An odyssey reincarnated across 80 years. Kraychik's necktie paradox led to Littlewood's card, then to Gardner's wallet game. The Alibaba problem goes one step further. Fill envelope A first, then flip a coin to put half or double into B. Once the symmetry of the setup breaks, exchanging can genuinely favor one side. How the envelopes were filled changes the answer. Pin down 4 assumptions and Monty Hall ends cleanly at 2/3. 2 envelopes is different. Only after passing through finite, conditional, and infinite do you see why even geniuses couldn't wrap it up cleanly. The grand finale. Starting from 2 envelopes, 3 separate roads led us to the same truth. Unopened break-even. Opened with a finite expected value, 0 gain. Infinite distributions. No comparison possible. In Monty Hall, what fooled PhDs and Paul Erdos was a silent assumption. In 2 envelopes, a faulty symbol. The moment the letter A was given 2 rolls, the mirage of a 25% free lunch shimmered into view. Hold on to the 10,000 and 20,001 fixed before the game instead of the symbol, and switching is just a fair coin flip. This isn't a lesson just for envelopes. In the world of data and models too, every time you name a variable, you should be suspicious. The neighbor's grass looked greener not because of mathematics, but because of an illusion. Real mathematics answers calmly. The next time someone claims a 1.25 times advantage, quietly ask whether that is a single amount. If you enjoyed today's journey, support us with a subscribe and a like. See you at ELLS Lab for the next Odyssey.